And we're going to move from a single independent variable, which is sometimes referred to as univariate, and we're going to move over to multiple independent variables, which is another term for multivariate, okay? And so, and thus, that's the reason it's called multiple regression instead of ordinary least squares or linear regression. Everything all right? You got one? Yeah. Did you have some questions on the class or no?
It was pertaining to class.
Oh, good. Oh, okay, 15. Oh, yeah, okay. This is actually module, I thought I had that up. It should be module 5. It's up on your computer screens that way, or in your in Canopy that way is module 5. And by the way, where I got a lot of this from, if you still have your old textbook, the BANA 1 text, a lot of the slides, a lot of the material that I use here, I use it to supplement what is provided in this for this specific text. Okay, so what we're going to talk about is we're going to keep working with a least squares sort of discussion and underlying principle, and what the underlying principle being that you want to minimize the error as you define this line. And we're going to test for significance just like we always do. It's going to be a little bit different here when we start using the p-values and the t-values and f-values, okay? And more specifically, the f value is going to be used for the overall model. So the p-value associated with the f is for the overall model. Is the overall model significant or not? Then what you need to do is you need to dig one level further, and some people picked this up the last time, is that there's another section of the output from Minitab, or really any software package, analytic software package, where it talks about the individual variables and their significance and their contribution to the overall model itself. So if you get a p-value associated with a variable or an independent variable that is over 0.05, then that variable has no effect, no significant effect or relationship to the model itself. So what you do is you drop it. And then you rerun without that specific variable in there. And then you'll get a pure model. So we'll talk about all those things. And so we're going to test for significance, and we're going to create a regression equation, a multiple regression equation, okay? Before we had one line, one slope, and one y-intercept. Well, now, with all these different data sets and all these different, not data sets, inside the data set, you're going to have different variables, much like you did in your case. You had percent of classes under 20, okay? You had what the graduation rate was. I think so there were several variables in there, and each of those has a line, a straight line associated with it, right? So what multiple regression, the technique using least squares, okay, and a little bit of ANOVA mixed in because you're trying to minimize the error and create a best fitting line for all the best fitting lines. Does that make sense? All right. And so then, and that changes the equation a little bit, because instead of just having one variable, one slope as part of the equation for the line that best fits the data and all the 2, 3, 4, 5 different variables, you now have a b sub 1, a b sub 2, a b sub 3, or b if you're looking at a sample, and beta if you're looking at an overall population. And you'd also have, of course, you have x1, x2, x3, x4. Okay. And then you can use this, and this is what we'll talk about. I think the next module coming up is about time series, and you can forecast or you can predict what the value or the expected value of y is going to be based upon all the different inputs or all the different variables and their values, in order to determine what is the expected value of y at a 95% confidence interval, because we're going to still run this at a sig, it's going to be a sig.05, a p.05 sort of testing that we're going to continue to conduct. And then this is a a categorical independent variable. And what I mean by categorical is 0, 1. 0 and 1 is kind of the quintessential example. It's either yes or no. Okay. You can also have categorical. What would be another categorical sort of condition or data set? Anybody have any ideas on that?
Would be like color.
Color. Oh, yes. Those are categories. Yes. Categorical. Okay. And so we're going to look at how you use these. They're kind of called dummy. They're called dummy variables in some respects. Okay, especially when you get down to a 0 and a 1. And how do you include those in your model? And then we're going to be able to interpret exactly what effect each one of these variables has on the outcome. And we're going to create that. We're going to create a more complex causal model. So rather than having just what we used last week, sales was the outcome, and I think advertising. Rather than having just advertising and sales, what were some of the other things we talked about that could influence sales other than advertising? If you recall last week, price. Exactly. What was that? What else was in there? Reputation, the brand. Okay. I'm sorry. Location. All these things. So now, what you're going to do is you're going to take all those variables and you're going to put them into this equation and figure out what is the best fitting line of all the best fitting lines. Okay? And one of those can be a categorical value, which would be 0 and 1 is the quintessential example, yes, no. The other ones are color or anything, but it can be a Likert scale. By the way, Likert, just so everybody knows, is Likert, and so that's a guy's last, it's a guy's last name, so it's capital Likert. The other thing that's going to become more and more interesting is a residual analysis. How much is left over, okay, that's unexplained by the model. And so you can figure out how much is left unexplained by that specific variable and how much influence it has on the overall model by the understanding of the lower the residual value, okay, the lower error you have for that specific variable, okay, the more contribution it makes to the significance or to the value or of y, or the expected value of y, and the overall model itself. So there's going to be a lot of things going on here. Before all we did, we went in, we said, okay, on the linear, really simple. That's why it's called, in some respects, it's a little bit of a Schulteism, ordinary least squares, okay, and so now we're getting into something that's not as ordinary. In fact, it's a little more complex. And that's what this module 5, it's from chapter 15 in the BANA 1 text, but it's module 5 in our course here. And then we'll cover logistical in the specific discussion. Talked about all these. And so keep in mind, anytime you are dealing with a sample, okay, or anytime you're dealing with a best fitting line, regardless in some respects, whether it's a sample or a population, you're always going to have some error in a multiple regression sort of analysis, always. So you always need to consider that epsilon or add that epsilon at the end if you're not trying to determine the expected value for y. Just saying y hat is equal to you got to add that epsilon at the end to continue to account for the error that's left over that the model or this line, this best fitting line of all the best fitting lines, does not explain. Okay. And here's what it looks like. B sub 0, you still have just one y-intercept, okay, but it's kind of a blended y-intercepts for all the y-intercepts from the different variables. A little bit of a Schulteism there, so be careful with that claim. But that's essentially what's going on here. And then what it does is you create this slope, slope, slope for every variable within your data set that makes a significant contribution to the value of y. All right. epsilon, this kind of goes without saying in some respects, but epsilon is a random variable as well because it's created by random variables. Okay? And we refer to it as the error term. So you see here where we dropped off that epsilon out here, correct? Okay, but you added in here the expected value, and so now you're looking at the expected value, and we're going to look at, especially when you talk about sampling, we're going to look at expected value, okay, or y hat of a sample as it relates to an overall population. Okay. And here is the estimation process. You've seen this a number of times, okay? And in fact, in linear regression, it kind of stopped. Everything from here over was dropped off with the exception of the epsilon, of course, okay? And so now you're adding in all these different variables. This might be, this y is sales, okay? We talked about advertising. We talked about price. We talked about location. And we talked about several things, right? And so now the key here is just like with any inferential statistics, do you have to go out and sample all billion people or crash every car into a pylon in order to determine what its safety rating is? No, you take a sample. It's just a lot of times it's destructive to do the sampling, and most of the time it just doesn't. It's good enough. It's good enough for what we do in business, okay? Because there's no such thing as perfect information. By the time you get perfect information, the market will have probably passed you by. Okay. So now you create these sample statistics. All right. And so you go from expected value of y to y hat, and then you're going to create these slopes, okay? And then the estimates, okay? And so here again, what we are trying to do is minimize the error as it relates to y with the variables x1, x2, x3, x4 as the input or predictor variables. And same here is that inside Minitab, when we get there, we'll do that on Thursday as normal. When we get the Minitab on Thursday, and you'll be doing an exercise, and then you'll work on your cases, it's called a response variable. The outcome variable y is called response inside Minitab. And these are coefficients. The slopes are coefficients as normal. And what we're going to do is we're going to make some assumptions based upon these coefficients. Much like we did before, we said b sub 1 was equal to 0 or not equal to 0. And if it was equal to 0, did you have a relationship? Was there a relationship that was significant or not between the x-axis and the y-axis of the independent variable and the dependent variable? Was there a relationship if it were 0? Right. And that's the null hypothesis. The alternate hypothesis is that there is a slope. B sub 1 in that case did not equal 0. So now we're going to investigate all these different slopes and what those relationships look like as far as understanding how significant a model is, or how much explanatory value we'll go to a coefficient of determination here too. You'll get explanatory value as to how much of the outcome y, the response, is accounted for by all the variables, and then you can actually go in and determine of all the variables that do have explanatory value what effect they have in an order of magnitude. So this is a programmer's salary, okay? And what we're doing here is we're taking a look at years of experience and the score on an aptitude test. All right. would you expect that this is a programmer, this is a series, kind of a geek sort of person, okay? Would you expect that the more years of experience that person has, the more money they make, the higher their salary? Sure. Would you expect that on an aptitude test, okay, let's call it a computer aptitude test, if you will, or a programming aptitude test, would a person who does better on that aptitude test make more money or not? In general, probably. But those are the type of things we're going to understand. And then we take a look at not only each individual, but we'll say, okay, what combination of experience and programmer test scores make for the best salary? And then a couple people can use those. Who could use that information as an employee or an employer? What would an employer do with that information that's wanting to hire IT people? They'll know what to look for. What would be any HR people? What else? What else could you take from that information in order to make a better business decision on? There you go. Are you paying the existing staff too much? Okay. Anybody else want to take that? Tyler, Mark? Yeah, go ahead. There you go. When you're hiring in, yeah. And likewise, if you're an employee and you're out in the market, which we're at 5.6, 5.7% unemployment right now, right? And there's a lot of unhappy people because there's been a lot of pent up going, wow, I've got to put up with the boss for another 2 years until this recession ends. Well, the recession is, they claimed it was officially over in 2009, but I would think that right now it is officially over. Unemployment is down. The American people are happier with the president. Therefore, I think that we can officially declare, outside of what the economists say, that the recession that started in 2007. Think about that. Wasn't that 2007? No. Yeah, 2007. Yeah. No, it was actually 2008. The fall 2008 when the ship hit the sand, so to speak. Yeah. Yeah. So we've been doing this for 7 years now. Okay. So what that means is a lot of people are going to be out there testing the market to see, okay, what am I now worth? Because the pay raises have been few and far between for a lot of people over the last 5 or 6 years. Now it's a seller's market instead of a buyer's market. So that's what an employee could do. Any other thoughts? Austin, Ashley, anybody? Anybody got any other thoughts on what you could use with that? All right, so let's keep pushing ahead. So you take this aptitude test, and so we're going to create a relationship. We're going to measure Y, the outcome variable salary, in thousands, and we're going to take 20 programmers from where would you take a sample of 20 programmers if you are the HR person trying to understand what you should pay a new person coming in? Where would you get your sample from? Benjamin. Isn't there a Benjamin here? No, maybe not. Must be the other class. Was it? No, there's a Benjamin in the other class. I'm almost certain. Yeah. Anybody? I'm sorry? A competing company. Yeah, you could go to a competing company. And you could ask their HR people, hey, you could go to 20 different companies and you could ask them, hey, based upon, give me just one person and what's their years of experience and what's their salary? Right? Where else might you go to get a sample? You could go internally, that's right. Is 20 enough for what we're trying to accomplish here? 20 programmers. Is there some source of invalidity here? Yeah, sure. 20, there might be a source of invalidity as driven by you might not be able to accept the assumption that you have normalcy of distribution because your sample size is only 20. So here's that data set. So here are the years of experience. Here's the test score, and here is the salary, right? And for all 20 of those. Okay, what's the mean, mode, median, range, and standard deviation for that data set? Trick question, all right. So what is the best fitting line? What's the slope? Okay, you got nothing at this point. Although you can, I don't even know if you can you pick out a trend? Here's 100. There's a test score of 100. They make 43. Where's another high test score? Here's a 91 that makes 33. 33.9, yeah. Yeah. Yes. That's right. Ah, we have an out. Oh man, I'm gonna send you flowers on Valentine's Day. You keep talking about outliers and stuff like that. That's great. Yeah. And what is an outlier? A potential golden nugget, or it could just be a total error. Okay. We come in here, and so we're going to name our variables x1 and x2. X2 is the test, the aptitude test. X1 is the years of experience, and years of experience, I think, let's put a range of 0 to, as far as defining the years of experience, let's put I think they're whole numbers, so they're integer, and they range in value from 0 to 50. Okay, and the aptitude test, what would be the range on that aptitude test? 0 to 100, that's right. And so you've defined your independent variables, and what is your dependent or outcome variable, y? Or your response variable if you're looking in Minitab. That's right. And so this is your theoretical regression model. You have y, and then we haven't talked about samples yet, so we're still in beta. Beta sub 0, what's beta sub 0? That's your y-intercept. That's your constant. Okay, if you're looking at Minitab output, remember that? Now what's B1? What's B1? Our beta 1 here. Heather. What's B1 here? Our beta 1. Yeah. That's right. That would be the slope for years of service. If you didn't have this piece out here, that would be its individual slope. But it has a slightly, each of these factors, or no, let me not use factors, each of these variables is going to affect the slope of all the other variables, so you're getting this blending. This is a little bit of a Schulteism. You're getting a blending of all of the slopes and all the y-intercepts into this one, okay, equation to define what is the best fitting line that helps you better understand the relationship between your independent variables, multiple regression, multivariate, okay, as it relates to how much you should pay somebody. That's what we're doing here. Okay. And because there's no expected value of y over here, you got to put in that error, because no line is going to perfectly describe, for the most part, let's say almost never, will have zero error and will always define exactly the relationship between, especially when you get into 2, 3, 4 variables, between all the variables and the outcome variable of y. And here's what we're going to get. We're going to, this is all the input data, okay, and this is sampling data. We're going to computer package. What's the computer package we could use here? You could use actually, Excel does a halfway decent job at multiple regression, but what are we going to use? Yeah. I may demo Excel someday, just not someday, but as we go through some of these things, just to make sure you know that you can do much of this in Excel. But here again, when you get into dichotomous response or outcome variables, otherwise known as logistical regression, Excel just falls apart. Now, Excel is conversely, Excel is excellent at graphing, which is probably it's stronger at graphing and charts and things like that than a Minitab, because it was designed to be more of potentially more, again, this is a Schulteism, potentially more of a presentation sort of tool than a number crunching tool. And then you get this R squared. That here again is a very, very powerful number, I think, in that you can take that R squared and you can find out all of the variables or all of the inputs, all of the predictors associated with any outcome. And so what that means to us as business people is that, for example, the CEO of a company, if the CEO of a company knows, and we've talked about all this before, is that what determines profit or what determines sales, and that person is able, that person or through the corporation or through the analytics people is unable to understand what effect each variable or each input has on sales, is that good or bad? Good. It's outstanding. It's great, because then you can predict what your top line revenues are going to be next quarter, next year, for the most part, and beyond, if you want to take the inferential model that far. At some point, though, it falls apart because of you have history that comes in that causes invalidity. And a typical history would be if this time next year we're at war with Russia. I mean, that would be a source of historical invalidity, okay, or a periodic event, okay, that occurred as we were doing this research. If you're selling, let me think, butter, okay. Let's not take butter. Let's take luxury vehicles, or not. Let's say non-luxury vehicles, kind of high-end vehicles. And there's a war in Russia, and everybody's currencies are beginning to waver and begin collapsing because the world is at war. Okay, are the sales going to increase or decrease for the automobile manufacturers? Most likely decrease. Okay, did you see that coming? Yeah, you can kind of see it coming, but how do you put that into a model? All right. Now you might put in your annual report, say, hey, with the conflicts, and this is what in the footnotes of a lot of annual reports they'll put in there, hey, if things go, I don't know how you'd say this, but if things go crazy over in Eastern Europe, all bets are off. And in fact, any contracts people, anybody want to be an attorney here? There's a term called force majeure inside every contract that is written in the United States, for the most part, or it's implied. And force majeure is a nice way of saying, it's a French term, it says if disaster hits by either, they call it acts of God, okay, or by insurrection, war, famine, all bets are off on this contract. The contract becomes null and void. Every contract, every substantive contract has that. Look for it. F-O-R, force, and then majeure, M-E-J-U-R-E, majeure. Sounds like a wonderful term, but just means, whoa. If the world goes to hell in a handbasket, anybody heard that term before? Good. Okay, where are you from? Ohio. Oh, good. Great. I can use a Missouri term here in Ohio. All right. Hell in a handbasket. All right. All bets are off. This contract is null and void. Okay. And here is the output from any statistical software package for the most part. It's always going to have this constant. And what is the constant? As we know it in the equation, y is equal to b sub 0 plus b sub 1 x sub 1 plus b sub 2 x sub 2 plus a little bit of epsilon. B sub 0, that's right, constant. If everything were taken to 0, you would still have this coefficient, okay, in that equation, yes? There would be, but you got to be a little bit careful because it's hard when you'll get an R squared for the overall model, and you'll be able to understand there's other outputs that you can begin understanding what the relationships are, but taking a direct R squared and plucking it out of a formula is I'm not sure how accurate that's going to be. Okay, you can do it. Okay, and you can isolate those r squared values, but I'm not sure how much meaning there's going to be. So that's why we come in here, okay, and we say this constant. We don't really, by the way, we don't usually worry about the p-value associated with the constant. The constant's the constant. What we look at is here, okay, experience. What's the p-value for experience? When you see something like that, you won't see this in Minitab. 1.9 to the minus x, no, to the minus 6. Is that a big number or a little number? No, it's not, I wouldn't say it's negative. It's very, very small. That means, this means you got 0.000000. Hold on. Point, what? 0.000019, I think that's where it would be. Yes. Okay. And so you would say that experience, okay, experience has a significant effect. In fact, you're 100% confident that experience matters. And you've got this here, this coefficient 1.4. What's 1.4? In our equation, y is equal to b sub 0. Oh, we're doing betas here? Well, let's do b sub 0. B sub 0, b sub 1, x sub 1, b sub 2, x sub 2, b sub, and plus some epsilon. What is this coefficient right here? That it actually would be the coefficient to x sub 1. That's right. That is your b sub 1. That's right. But it's your coefficient to x sub 1. So you're in the right church. Okay. Now you might not be in the right pew, but you're in. Anybody? Is that another one? That's a Catholic thing, I'm guessing. Anyway. Huh? Your economics teacher says that? Yeah, there you go. What's his name? Her name? Farley? See, is it guy or lady? Guy. Is he from around here? He's from New York. Oh, there's very Catholic up there. All right. Lots of Italians. All right. Here we go. Now, test score, okay, is test score. Remember the aptitude test? Does that have a significant effect on our model based upon this p-value? Yeah. So here again, you go right for that p-value. All right. And this is the t, and the way you know that you're looking at the individual variables, okay, is that you have t instead of f. F is for the overall model, okay? And I think I've got a slide that shows that. Okay. See what else is going on here. Oh. So this is your equation that best fits all the two best fitting lines for experience and score as it relates to y, which is salary, or the outcome variable. This is it. Experience was x sub 1, score was x sub 2. So wonderful. Oh, by the way, you'd have a little, you'd put a little error in here too. Okay. And so you can predict. You can say, okay, hey, I got 10 years of experience. I scored an 85 on the aptitude test, and I get, somebody run that. Actually, you can run this. If you had an experience of 10 years and you scored 100, oh, this would be easy. Let's say you had 10, let's do 100, okay? If you had 100, that wouldn't be. Oh, let's use 10 years of experience and you got 100 on the score. What would your expected salary be in this equation here based upon the sampling? Okay? If the score was 100, what's 100 times 0.251? 25.1. What's what's 1.4 times 10? 14 and 25 is 39, so you're right at about 40. 43,000 would be your expected salary. What is your confidence level for that understand, or for that outcome variable where you just claimed it was 43 and some change? What's your confidence level? P.05, sig.05 as well, or you're at a 95% confidence level. Same thing. The only difference here is instead of just looking at experience and stopping there, we added another variable. Thus, we come back to the discussion, multivariate. Now, the good news is we also, based upon that equation, we can now make some additional statements about what is occurring between the relationship of salary score to the outcome variable salary. Not salary, but test score and years of experience to the outcome variable, response variable of Y, which is salary. And so what you can say here is that B represents, and I'm going to read this just to be specific, B represents an estimate of the change in Y corresponding to a 1 unit increase in X when the other variable, okay, the other variable is held constant. So what does that mean? So if your B sub 1 is 1.04, okay, and that's the only value you put in your equation, and everybody else has 10 years, everything else has 10 years of experience, so you hold that constant, you freeze it at 10. No, this is 1.04, that was years of experience, right? What was the equation? 1.04 times experience. So you're going to, if everybody scored a 100% on the aptitude test, what effect can you say that years of experience has on salary? And this is, well, let's talk about that, okay? So for every year of experience, you can expect your salary to go up $1,400 and some change. This is and so what you're doing is you're saying, okay, for every 1 unit change in Y, which are in X sub 1, which is years of experience, and everybody scores 100, or everybody scores a 50, whatever the number is, you're going to get a 1.4 lift on salary. You got to hold the other one constant. You could take it to 100, you could take it to 0. I think in the text, the example we're going to be working on Thursday is you're going to take it to 0. Okay, so you zero out the aptitude, and so what is then you can say 1.4, okay, is the expected lift. It's kind of a lift, or it could be a downdraft if it's a negative number. Okay, and again, these are a little bit Schulteisms. A lift is not a Schulteism, but a downdraft is mine. Okay. Conversely, or not conversely, additionally, okay, and at the same time, if you'll hold years of experience constant and you zero out everybody's years of experience, zero it out, or take everybody to the same value for years of experience, okay, for every 1 unit increase in your score, you get a 25%, you get a 25, I think that'd be $250 increase in your pay. Let's see if that, a $251 increase in pay for each additional point that you score on that exam. And so let's take this more broad-based, is that if you know what effect, that if you add more advertising dollars or you put more ads onto the air or on social media or wherever your advertising you found is most effective, if you increase your advertising by $500,000, in theory, if you had a coefficient of 1.5, you would see your sales increase by 50%. So you're really getting into some powerful, powerful stuff here, because if you can understand, and based upon historical information, this is what economists do all the time. They sit there and some of these econometric models, anybody ever heard the term of econometric modeling? Okay, they're always wrong. Okay, economists are always wrong. In fact, I think last year they anticipated that inflation was going to be, I think the consensus was going to be 1.8%. What was our inflation last year? It was about 0.8, about half. But all the economists in their models, okay, said 0.9. What happened though? What caused them to be way off as opposed to just a little bit off? Inflation. What happened to the price of oil and fuel? Yeah. Yeah, you bet. Anytime you drop fuel and oil, okay, that's going to reverberate or echo through the economy. Okay, when you have a price of oil, a barrel of oil goes from 100 down to 60. Does the airline make more money or less money? More. Could the airline actually decrease their prices from last year? Yeah. Okay. There was one in the here was one. This is kind of a little really in the this is really kind of trashy. This discussion here is that who's the Rumpke? See, hit that Rumpke trashy. Yeah, it's kind of this is kind of a garbage discussion. But Rumpke, if you've ever seen your trash bill, okay, put a little surcharge, fuel surcharge on there. Now, and that was when gas price a barrel was what 120, 130. Did that thing go away? No, you bet. Yeah, it's kind of like taxes in some respects, but they're getting on them now. But that price, in theory, it did go up, and it actually could have gone down. So inflation, kind of a very colloquial, pedestrian sort of example. The inflation on the price to get rid of your trash theoretically went down last year. And Rumpke, instead of passing it on to you, they put it in their pocket. Is that good for the economy or bad for the economy when corporations make more money? It's darn good, in theory, because then they can go out and hire more trash men or more business analytics people to understand the trash business, because the trash business is always picking up. Actually, I didn't get. By the way, I had that one for a number of years. Yeah. I'm gonna give it. Okay, my dad he owned his own business, and he owned a parking lot sweeping business, and so that was his tagline: "Business is always picking up in my business." So I don't know. So I'll source that one. That's good. That's a good 50 years old. That one there. Well, anyway, you can see here, you do the same thing before. You add up all of these, and you're doing an ANOVA analysis, and so you're minimizing this variance, and you're creating the best fitting line to minimize the variances for all of the data for each of those variables. And you can imagine how complex this would be when you start running those things. Okay, and you're in a econometric model, and you're trying to understand what GDP is going to do next year, or you're Procter & Gamble, and you're trying to figure out how many, what was it over in Russia that just went through the roof? The price of tampons and toilet paper. I mean, it's gone through the roof. Okay, people are buying less toilet paper in Russia. Okay, now we could take this one another step further if anybody would like to add to their a comment on that one. But regardless, what we're going to do there is, so you'll know what the variance is that you're trying to minimize to create the demand for any consumer product, which is easy. Not easy, but there's at least, you could probably pick out 20 factors or 20 variables that would have an influence on the sale of, let's pick something a little less colloquial or pedestrian or controversial. Let's pick up paper towels. Okay, do people buy fewer paper towels or less paper towels when they're unemployed? Probably, but you could test that, and you could say Procter & Gamble or anybody who sells any product could say, okay, if GDP does this, what is going to happen to my towel sales? And then you take that in your causal model and you push it into profit. Okay, and now you've got a nice causal model. You've got all those relationships, and you as the product manager, or you as the CEO, or you as the group brand manager, okay, or the CFO, chief financial officer for a large corporation, can figure out what's going to happen next year with some level of confidence. Okay. Now again, you have these episodic events where the price of oil collapsed. Okay. And actually, you could have seen that coming because all the shale wells, the fracking that was going on, all the fracking on all the shale drilling that was going on up in the Dakotas. Okay, you should have seen that coming if you didn't. Okay, not me, but others. Okay, so now you get your overall model, and this is where you look at the F value. If you get T and F mixed up, you might be making the wrong decision, because just because you get an F value for the overall regression model of 0.00 doesn't mean that every variable inside what you've analyzed, okay, the number of variables, you could have 10 of them and only 8 matter, okay? It doesn't mean that all 8 of them matter or all 10 of them matter. It just means that the overall model is significant. Now, when you look at that overall model and you take out a couple of variables that don't matter, what happens to your error? It's going to go down. That's right. Because you're taking out a couple of variables that don't matter, you're making a cleaner model. You're able to understand what's going on inside your business, inside your factory, inside your marketplace, on and on and on. Okay? And so that's a great thing. It's a great thing to know what's going on inside your business. And it doesn't matter whether you're a public company like a Fifth Third, or whether you are a private company that's out working with investors or a board of or a venture capitalist. Doesn't matter. They're all wanting to know, do you understand your business enough where you can tell us what sales are going to be like next quarter, because you're in here asking for another $100,000, $200,000. This is a small business. This is entrepreneurship. You're in here asking for another $250,000. Now, help me understand this. You missed your mark last quarter. What happened? And now you want me to trust you again for next quarter that you say you're going to hit these numbers and I should give you more money? Seriously? Okay. Now, if you hit your numbers last quarter and you didn't blow them out of the water too much, or you didn't go too far under, and somebody comes in and says, hey, I'm going to need another 250. Be 250 million, 200,000, whatever, 2 million. Okay? Are you more inclined or less inclined to give that person money if they more accurately predicted what their business was going to do in the next quarter? You bet. You're going to give them more money. And that's exactly what the stock market does. That's exactly what Wall Street does. That's exactly what venture capitalists do. Okay? And that is the essence of running your business. Now, do you always do it by the numbers? No. Okay? You take into account, as we've always discussed, right, is you take into account your experience, your gut, and you say, hey, this thing over in Crimea is going to be a problem. Okay. The inflation rate in Russia is going to be a problem. We're going to get hit. Now, this is a legitimate one that you could say, hey, we're going to have, especially consumer durable goods, but consumer packaged goods, okay, like the things we've already talked about as far as paper towels. If they get more expensive in Russia, are people buying or not buying that product as much as they did before? Economics, right? What's that guy's name? What's the guy's name? Barley, yeah. Supply and demand, right? Supply goes up, price goes down. Demand goes up, no corresponding increase in supply. Okay, you're going to get a price increase, and that's what's happening. And there's lower demand, okay, but there's a much lower supply going on, and it's more expensive, and so that is and that money is more expensive because of the exchange rate. A ruble is worth half of what it was when they're buying a paper towel from somebody from P&G than it was a year ago. Just doesn't buy as many paper towels. Now here comes back to, not only can you understand everything that's going on inside your causal model, and I'm going to draw this causal model up, and basically for those who are listening on the video, I'm going to draw 2 circles and a third circle. And the third circle over on the right is the outcome, the x sub 1, the x sub 2, and there's an arrow that goes here to there. And what's x sub 1 in this model that we just examined? Experience. Good. What is x sub 2? The test score. Okay. What is y, or the response variable? salary. Okay. And sometimes you'll actually see some correlation numbers here. For example, I don't know if experience is pretty strong actually. So I'd say that was probably experience was about a point, probably about a 0.8. You might see that written along the line as an R. R equals 0.8. And this one was yeah, that was probably might have been again, I'm just making up these numbers, an R 0.5. But combining the two together, and you can say that this is on a non-adjusted basis, by the way. I'm almost certain. Yeah. On a non-adjusted basis, what are you saying here as far as the influence that experience and aptitude test score combined have on the outcome variable y? What can you say about this R squared value? That's right. Say that one more. That was great. Levi, again, you're going to get flowers too. I mean, you and Jake are going to get like Valentine's Day, right? Yeah. All right, go ahead.
Your test score and your experience account for 83% of your salary.
That's right. Combined. That's right. That's right. And here comes back to the question that Mitch had. Can you break those out? That's why you hold one constant. That's kind of why you hold one constant, and because you're somewhat understanding the influence that each one has, and there's another term that's called studentized beta, where because you're not comparing apples to apples, you're comparing apples to oranges. But there's another technique, and this is a little bit beyond what we're going to talk about because Minitab doesn't provide it, and it's really not all that important right now. But there's what they call a standardized coefficient, okay, or studentized coefficient, where you can actually go in and compare apples and oranges, okay, because it puts it on more or less an index. But that's beyond this course. So, but you can clearly say those two factors have, as Levi said, an 83% of the reason you have a certain amount of salary can be accounted for by years of experience and aptitude. Does that make sense? Yeah, it makes sense. That's exactly right. Exactly. That's what's left over. That's what's unexplained by your model, and that's not the epsilon value per se, but what's not represented here as far as 83% is roughly 17%, and no, actually 16% and some change, right? That is left unexplained by this model. Now, where might that be coming from? What's another variable you could put in here to better explain salary? Depends on the company. Say again. When they were hired. Yeah, if the economy was when we did what? We did a -6% GDP in I think it was the second quarter of 2008. Okay, when GDP is going like that, and you got unemployment of 11%, and you hire somebody, are they going to make more money or less money than they would today at 5.6% unemployment? Less. So that might be a factor as well. So you might look at their hire date. Now, if you find that the hire date had a lot of influence on that person's salary, okay, and they're making significantly less, okay, this is where this is HR. This is what they do. This is what they're running numbers, and that person's making significantly less, and they got 100 on the aptitude, and they got 10 years of experience. What do you got? Yeah, that employee, if they're a good employee and are good, especially a good programmer these days or a good IT person, you'd better be in there helping them out a little bit, okay? Because they're most likely, especially these days, if they're that far underpaid from the market because they came in at the wrong time, they're probably a flight risk or a turnover risk. And you lose a good programmer, or you lose a good ops person, or you lose a good person anywhere. And is that good or bad? It's bad. Okay? And that just costs the company money. So, anyway. So now we have this, what's called an adjusted R squared. Okay, and what we do here is we take into account how many variables are in. It's a really, again, a somewhat complex formula, and you can calculate it. But basically, what you're doing is you're accounting for how many variables your model includes. Okay, and then you're adjusting. Okay, so the more variables that you have in a model that are significant, the wider the gap will be between your B value or your slope, your coefficient, okay, and or the R squared, and the adjusted R squared. Okay, and I think they probably bring that out. Well, here's the value. I mean, standard square of the treatment. Okay. And again, as we've talked, it's based upon it takes into account how many different independent variables you have, or not how many different, but how many independent variables you have. And it's probably, I think you can make a pretty good case that R squared adjusted is more accurate than a straight up R squared. And here's another formula for it, on and on and on. Okay. And you get a little bit of an adjust here, and you can see there's N, okay, and then there's P, which is how many variables you have, I think, in this situation, all right? And you had your original R squared, and that's the actual formula. But again, you don't have to worry about this. Just know that there is a formula in there, and that the reason you have an adjusted R squared is because it's probably, it most likely is a little better number to use when you're trying to understand a causal model and how much influence the model has, or how much of an explanatory value, as Levi mentioned, how much of an explanatory value you have relative to the outcome variable y. And this applies to any equation. I mean, we're just using the aptitude test and salary and what have you here. And that's the great thing about this. And this is what, remember when we talked in Bana 1, how we took everything to the common currency of t, or the common currency of f. These could be any set of variables, okay? Or these could be any units associated with variables. And in fact, you can take those units that look like apples and oranges, and there's a technique where you can even studentize or standardize those to create an index to even further understand how much of an influence each of those variables has on the outcome variable y. This is incredible stuff. I mean, I don't mean to get too excited about this, but this is what we used to do by gut. Companies used to do this by gut, and now, today, there is almost no company, no organization of any substance that at least does not take a lot of this into account, or does not consider it. Your gut, your experience, on and on and on, but it's just as important to know, okay, is what you have, is your model correct or not? Can it support your gut? If it doesn't support your gut, okay, if the model you created doesn't support your gut, and the model is saying we're going to increase sales by 10% next quarter, and your gut's saying, I don't know, what might you do? You'd give it a haircut. That's what, again, no, never heard that term. That might be more of a business term. You give it a haircut, and you say, okay, instead of 10%, I'm going to go 8%. But your gut is tempering that a little bit, because you're going, I hear what the model's saying, but this thing in Greece getting ready to pull out of the European Union. Man, I don't know. If that happens, there's going to be a problem over in all of Europe, not unrelated to Russia potentially, but probably. But there's going to be a problem there, and so our sales might soften, or we might find that the European economies are not going to come back as quickly as they are expected to. And what happens if half of your sales is based upon the European economies, and it's going to soften, and you apply your gut feel based on what you know about world events, episodic events that might be coming up, and more specifically, Greece pulls out of the European Union, people get less confidence in the euro, You go, Conversely, if you're looking at it and you go, I'm going to guess that unemployment is going to be thus and so next year because I make decisions based on unemployment, housing, no doubt. If people have more jobs, if less people are unemployed, do more houses get sold? Yes. And if more houses get sold, do more refrigerators, durable goods, and draperies get sold? You bet. First thing everybody wants to do, again, this is probably a little bit, first thing every spouse wants to do, I'll put it in the spouse category. First thing every spouse wants to do is change the curtains. I mean, it's just inevitable because the person before them, it wasn't the same taste, okay? Yeah, and so, and this is really important to make sure you know this or understand the differential here, is that in a simple linear regression, the F and the P, or the F and the T, and the p-value that you see there applies to the overall model and to that individual variable, okay? But when you get into multiple regression, okay, you need to look at the p-value associated with the F. You're still going right for the p-value, but you got to know what p-value you're looking at, okay? You don't want to pick the wrong p, right? And so when you see the F, you look, and what you look for is you look for the F and the T, and then you look to the right on most reports, and you'll have the p-value. Sometimes the p-value is to the left. I think SPSS has it to the left, but it doesn't matter. Just look for the p-value. Make sure you pick the right p. Okay, let's talk a little bit about some assumptions. Okay, and remember we talked about normalcy of distribution. If you don't have normalcy of distribution, can you run a linear regression? No. Okay, you have to go find, that's considered a parametric test. If you find that you don't have normalcy of distribution, okay, you'll have to use a non-parametric. Now, if you find that these variables are not independent, okay, in that not that one doesn't have an influence on the other, but just that you're not kind of measuring the same thing, okay? If you're measuring, here we go. If you're measuring unemployment and GDP, okay, are those two variables independent? Not completely, okay? So that's a good example. If you're looking at test scores, you use, here we go. Variable 1 is test scores. Variable 2 is grade, alphabetic grade. Are those two variables independent? Not even close. Not even close. Okay, and there are varying levels of independence, and we'll talk a little bit about that as well. So those variables have to be as independent as possible. Okay, you're not always going to get every variable is independent, 100% independent of every other variable, but you can run a test to see, okay, is it close? Okay. Okay, talked about that, and in fact, what you do here is keep in mind that you're not only doing ANOVA analysis, regression analysis, you're running individual t-tests on each one of those variables to figure out if they're significant to the model or not. How long would that take you if you have just five variables and a sample size of 100? You're going to be here for a week. Especially if you're trying to, it might be longer, and by the end of that week, you might have gotten the wrong answer because you had a little glitch back here. All right? By the way, if you do that on the exam, you'll get partial credit. If there's a little, I look for partial credit, or you'll help me on the first one, look for partial credit, because if it was just, you just added or subtracted something different back here, and it flowed forward, I do take that into account. Okay, so partial credit is available on the exam. As it would be in real life, I suppose. Yeah. Okay. and you're going to do a test for each individual significance. So here again, make sure that you're looking at the right significance value associated with the T or the F. Okay. And here's our hypotheses. There's no difference here. All right? It's going to be the exact same. All right? Here's your HO. Your slopes are all equal. If all of your slopes are equal to 0, is there any relationship between those 1 million variables? If you had 1 million variables and every variable in there was equal to 0 as far as the slope goes, okay? Okay. Is there any relationship between the outcome variable and those million variables? There'd be none. 0. Z, nada, net. No, if you're French. Here again, also, you're going to be looking at your F value. You're doing, it's the exact same thing as you've done, going back to the theory. And what I'm going to do here is I'm just going to draw up this theoretical, okay, the distribution curve. And we're going to measure this. This is an F value. Okay? And what I'm going to do here for those who are, don't have benefit of seeing the screen, I'm going to do my same old, and I'm going to do this on an F, okay? And we know F is equal, and this is on the x-axis, F is equal to MSR, okay, mean square of the residuals over the mean square of the error, boom, boom, boom. And you're going to get a curve associated with that F value, okay? You're going to create a critical value. It's the same thing you've done a million times. There's no difference here. Okay, just like we did with linear regression, just like we did with ANOVA, just like you did with T, okay, just like you did with Z. It's all the same, okay, and it's based upon the empirical rule, okay. And so you're going to get that F value, and when your F value is down here, you do not reject. When your F value is up here above your critical value, you're going to reject HO. And when you're up here, past the critical value of the F, what's your p-value most likely as relative to p.05? It's going to be less than p.05. Everything is exactly the same as what you've talked about before. That's why, in some respects, most of this is fairly straightforward, okay? And that's why each of these concepts builds on the other, okay? And you're going to go back. Remember the F distribution chart? The good news is the F distribution chart is loaded in the computer. You don't have to worry about it. It's going to give you a blended degrees of freedom. You don't have to worry about calculating that. And boom, you hit a button, and out comes this report, okay, based upon all the theories we have here, and all the underlying principles that we've talked about before. And so then you make a decision to reject your null, which means there's nothing going on. There's no slope, there's no relationship, versus at least one of those has a relationship, which is the alternate hypothesis. And instead of mu like we did on T and Z, okay, here we're using beta, or the slope of that line, which at some point you might have known was mx instead of bx in the old days of algebra. All right. And here's your rejection rule. Okay, and this is on the F. This is on the F, not the T. Same thing all the way through. One or actually when you're doing the alternate hypothesis, put one or more of the parameters is not equal to 0. Okay. A lot of people will say, oh, by the way, when you start using the term, this is why this is key in your hypothesis. A lot of people are saying larger than, less than. Okay. When you use those terms larger than and less than instead of equal to or not equal to, what would you have to do? Equal to is a two-tail analysis, right? Okay, and this is why generally we will default to a two-tail test, as opposed to a one-tail, Okay, and so if when you're doing your hypothesis or you're doing your questions, make sure it all links. Okay, and this is really important because if you sit there and say, "Hey, I want to figure out if one of these is greater than the other," what do you got to do? You got to go and run. You got to go and run a one-tailed test, and you have to change some of the settings. Okay, and you saw that. Remember, there was I think they used two-sided, right-hand side, left-hand side, inside, or within Minitab. All right. So that's why it's important that the wording, while it appears to be a distinction, okay, with no difference, in this case, it could have serious differences. Whether you create your critical value at P.025 or P.05. You're allowed to be off by a factor of 2 as far as what your error is. All right, so there you go, right there, the p-value as normal. F-test is for that overall significance, and you would find roughly that if you divided 250 by 5, that'd give you about 43. Do that number real quick. It should be dangerously close. There's going to be a little bit of adjustment in there for the variables. So you run that real quick. 250.164 divided by 5.85. Thank you for having your calculator, by the way.
42.7630.
Yeah, in this case, it's exact. Yeah. Okay, that's where you get it from, because here's the residual error. Okay, and here's your regression model as far as your mean square. Okay, don't have to know these. Just theoretically, this is what's happening in behind the computer that you would normally crank the numbers, crunch the numbers, but here, as we've talked about before, computers crunch numbers, people crunch decisions. And on that crescendo, I shall leave you to your exit. I'll cut that from the